Welcome to the last of our Monday lunchtime seminars, and today is a special one because it's 5 talks from our facilities across Imperial. So we'll hear from Sarah Fearn on surface analysis, Lisa Haigh on mass spectrometry and the Agilent measurement suite, Catriona McGilvery on electron microscopy, Irena Nevjestic on Spinlab magnetic characterization hub, and finish with Andrew White on small molecule crystallography. So we've got now facilities across materials and chemistry and the molecular science research hub as well. So these talks will be recorded, and hopefully that's okay for everyone here. And then they will be published later on. Since it's it's quite a tight schedule, so it's about 10 minutes for each talk. We'll just go through all of the presentations and then leave questions for the end. So please, for the audience, write down your questions or put them in the chat, and then we'll get back to them at the end on the time that's left over. Okay, I think that's it. So very welcome to all of you, and let's get started with Dr. Sarah Fearn on surface analysis. So,
okay, can I just check that you can hear me? Is that an okay, Sandrine?
We can hear you. We can hear you.
Right, so let's try and share a screen. Now then, share content, come on. Working. Okay.
Yep, we see it.
Okay. Right, good. Got the thumbs up. Okay, so my name is Sarah Fearn, as Sandrine just introduced me, and I work in what's called the Surface Analysis Lab here at Imperial. And, oops, I don't seem to be able to have any control here of changing the slide. Ah, there we go. Oops, right. So, in the Surface Analysis Lab, I'm going to focus on 2 instruments that we have here that are actually combined, and that is the INTOF time of flight secondary ion mass spectrometer here on the left, highlighted in blue, and on the right-hand side, highlighted in white, is the INTOF QTAC low energy ion scattering instrument. So the difference between the 2 instruments is one sputters your target material into a mass spectrometer to analyze, and the other one scatters a primary ion beam off the surface to get data. Starting off with the time of flight secondary ion mass spectrometer, the specifications of the instrument are that we have a primary ion beam of bismuth and sputtering ion beams of oxygen, argon and cesium, as well as an argon gas cluster source. And this is quite important to have these different ion beams depending on the material that we are looking at. There's also heating and cooling available on the instrumentation. So just quickly to go over what SIMS actually is, what we have is ion beam bombardment. So we have a primary ion beam gun here that comes down, rasters over the target, causes sputtering and ionization of the material, which is then collected into a time of flight secondary ion mass spectrometer. And then we get different outputs. So we can have surface spectrometry, where we do static SIMS, so it's non-destructive over the surface sample, and we collect a mass spectra. So do surface imaging. Again, we can remain in this static non-destructive regime, and we're rastering a finely focused ion beam over the surface, and because we can analyze the material in its solid state, we can get mass resolved secondary ion images. So here's just an example of oxygen and CNO and CN in different places to one another. And by introducing a second ion beam, so we have this sputtering ion beam that can also come into and raster over the surface, we can depth profile through a material and can get in-depth distribution of species that we're monitoring. So, some of the advantages of SIMS compared to other techniques, it's the only technique that can analyze all of the elements from hydrogen through to the uranium and their isotopes of the periodic table. So that's quite unique. We can also capture molecular species, And the information that we are obtaining this from is from a solid surface, so we're not having to turn it into a gas or a liquid, which means that we can do ion mapping. We've got the spatiochemical information during the analysis. The technique is ultra-high vacuum, so we get high sensitivity, high detection levels, and also we can do these analyses from the surface into the bulk, so we're going from nanometers down into many hundreds of nanometers if that's required. And also we can look at any material as long as it's UHV compatible and doesn't outgas. We can also look at insulating samples because we have strategies for overcoming that. So to whiz through a couple of examples, here I've been working on some age-related macular degeneration. So this is just an optical image of what's called drusen, which are calcium deposits, which are here, which form in the eye tissue and block photoreceptors, so commonly known as the cones, which you can see along here. And this ends up leading to blindness. So the people leading this research were interested in knowing the makeup of the drusen. They know it's calcium-based, but what exactly? And so what we can do with the SIMS is we can map that surface. So first of all, we get the mass spectra, and here we're up to quite high masses. And what we can see being captured here at regular intervals are calcium phosphate peaks related to hydroxyapatite. So in between each of these peaks, we're losing, going backwards, a calcium oxide unit. And along with capturing these calcium phosphate peaks, as well as just calcium, we can also capture the protein fragments associated with the tissue. And then once we have this data, we can pick out the individual peaks of interest and map that on the XY plane. So here we have the sum of the proteins that are captured, highlighted here in the tissue, the sum of the hydroxyapatite fragments, so the calcium and the phosphate signals here in this drusen region, and then we're able to overlay them to see them more clearly. So that's one area where this has been very successful. Very quickly looking through earthworms. So in this case, we weren't sure what we were going to be finding. So often we don't use SIMS to try and find things, but in this case, we've got an earthworm and it's sliced in half along the length of it, and we've done various different maps along here. So this is the other advantage with SIMS. We can go from looking at very small regions, 20 micron square, up to stitching images together, which are a couple of microns in size. By capturing the mass spectral information from along the body of this earthworm, we were able to identify this Dryla defensens, which is a compound which was understood to enable the earthworm to be able to digest pine cones, because people were unsure how earthworms have managed to survive in North America. And the benefit of this work in SIMS is that we're doing it label free, so we're able to identify these enzymes without doing any labeling. So that's quite a useful thing to be able to do. This was published back in 2015. A bit more biological work here. We're looking at silver nanowires in cells. So these cells were critical freeze point dried, and we can see an SEM image here where there's a cluster of cells. And these are bright sparks, which is where the silver is situated. And then we've been able to map this again in the SIMS, and it's label free. We've been able to see the protein fragments, which clearly identify the cells on the surface. And what we were looking for is to look for these sulfur-based enzymes to see whether the content of the silver in the cell was disrupting these enzymes, which are necessary for good lung function. So we can see quite nicely the distribution as well of these sulfur enzymes, and along with a few ion signal from the silver ions as well. So these are very small area now. So going from a couple of millimeter there on the earthworm to these very small cell structures. And then again, we're overlaying the maps to see where the distribution is of the silver, the cystathionine, and the proteins. So again, working very nicely in correlation with SEM here to try and identify processes happening on a biological level. Looking at some 2D materials, this is work carried out with postdoc Taylor Stock and Neil Curzon. So here they're coming up with strategies to do silicon overlays on their arsenic delta layers. So an arsenic delta layer is one atomic layer of arsenic within the silicon structure. So here we're really exploiting the depth, high depth resolution of the SIMS here. We're going up to like 15 nanometers in depth and getting very nicely resolved arsenic peaks in those structures. and just some bog standard compositional depth profiling, very nice through a very complex oxide material here. Quickly moving on to LICE, low energy ion scattering. This technique is in this regime here. We're looking at the outermost atomic layer, and then we can get some signal from the background to look at a few atomic layers just below that. So very compatible with SIMS, very compatible with XPS here. Our specifications for the instrument, we've got high brightness, helium, neon and argon with a depth profiling argon source as well. We can also do plasma cleaning with oxygen and hydrogen so that we can really look at that outermost atomic layer. So we're mass sensitive, we're only looking at elements with this technique, no molecular species. We're looking at the outermost layer. We can see how coatings work because we can see the presence of pinholes. We can see information at the next 2 to 3 atom layers below due to the convolution of the spectra, and it's quite a fast analysis. So just quickly to go over the process, we have an ion that comes in, scatters off. Through the conservation of momentum, we can calculate what the ion actually interacted with, because we calculate the energy loss of the scattered primary ion. One example here, we did some nice work with some ionic liquids. Really important to know what's on the outermost atomic layer with these materials to see how they function. So this is what the spectra looks like, quite different to a mass spectra. Just energy along the x-axis and counts here. And so as we go along this spectra, what do the different peaks mean? These surface peaks mean that the element is clearly on the outermost layer. So what we're seeing exposed to the surface is fluorine. The carbon is hidden in a background signal, so not very clear, sulfur and oxygen. No nitrogen is identified, that's sort of below the surface. Just looking at an inorganic structure, looking at wanting to get strontium titanate termination wanting to get a TiO2 termination on an STO substrate. So we're hoping to get this outermost layer through etching and annealing, just get TiO2 termination, strontium oxide, and this is what the spectra look like. So etching and no anneal, we've got STO, no TiO termination. Even after the experimental work, we're still seeing the strontium visible on the surface. So this is really quick to identify that, and in correlation with high angle XPS, we can put what the content is of that strontium on the surface. Finally, we also have a 3D optical interferometer, this Zygo NuView, which actually, going back to the drusen, this was used to make the image of the calcium drusen in the eye tissue. We've got depth resolution of 1 nanometer, a huge range of magnifications, and we can go from very small to large areas with image stitching. So very good for tribological studies on surface, looking at craters, and also it's air-based as well, so very fast and easy to use. So that's it, a summary of all that we have in the lab currently.
Thank you, Sarah. That was amazing. Very fast.
Well, just 10 minutes.
So many results. Yeah, thanks very much. We'll move on to Dr. Catriona McGilvery on electron microscopy. And we can see you. And you can see your slides. Yes, that works. Thank you.
Can you hear me okay as well?
Yep, thank you.
Okay. Thanks very much for letting me talk about advanced electron microscopy. My colleague Mahmoud Ardakani gave a really good overview of our whole electron microscopy facility a couple of months ago. So I'm not going to cover all of that again, but cover kind of more advanced electron microscopy techniques, particularly in the transmission electron microscope. So Mahmoud and myself and Catty run the EM facility. And then James Douglas has joined us just within the last month. He'll be looking after the atom probe, and that we're going to be getting soon. And I'll talk very briefly about that in a few minutes. So these are the microscopes that that Mahmoud talked about when he spoke last time. And then we're going to be getting new equipment that's coming, which I'll mention in a little while. So these are the 3 TEMs that we have, a JL 2100 plus, the 2100F, and then the FEI Titan. And so we have different techniques on each of them. They're useful for different experiments that you do. We do quite a lot of, or we do some cryo work on the 2100 plus. On the 2100F, we have eels set up on that. And we also have particular apertures that can be used for doing bioimaging work, low-dose imaging. And you can also do a little bit of nanobeam diffraction on that instrument and tomography. And then on the Titan, which is kind of our upper end instrument, we have a monochromator, which means that we can get energy resolutions down to about 0.1, 0.2 EV. That's in comparison with the 2100F, where you'd be talking about an energy resolution of about 1 EV. We have an image corrector, and then kind of STEM and EDX and EELS on that system as well, and some basic scanning, nanobeam diffraction, and tomography set up on that. And so I'm just going to run through a few examples of where we have published work on this so that you have an idea of what can be done. So this is STEM tomography work. This was done with two of our former CDT students, Sophia Martinsini from Chemical Engineering and Josh Bailey from UCL. Boron nitride is used for a variety of applications, kind of including catalysis, gas-liquid separation, gas storage. And these guys were wanting to be able to tune the porosity of the boron nitride for the different purposes that they were using it for. And so using electron tomography, we were able to then take a tilt series through the sample and reconstruct those images to get a 3D picture of what that porosity looked like. And you can see clearly from these images on the right-hand side, just the tilt series being reconstructed, that they look very different. And then you can reconstruct the material or the information from that material and actually start to analyze the porosity within those samples. This is another example of a very basic scanning nanobeam diffraction setup we have, 4D STEM setup. When you hear people talk about 4D STEM nowadays, they're using much faster cameras, and they can acquire the data much quicker at much lower doses. But even on our Titan, we have a very basic setup. So this was work that was done with Alexandra Porter and Baptiste de Paul, looking at biomineralization of bone tissue. So this is our setup where we have our sample, and we have a nanobeam electron diffraction pattern. So we have a probe size of only about 6 nanometers, and we can then scan that across our sample and acquire a diffraction pattern at every point. From that information, Baptiste was then able to mask the diffraction pattern and work out what the orientation of the crystals were within his mineralized tissue. And so then he was able to create a map of that. So on the left-hand side here, you have mineralized tissue. And from exactly the same region, you have some of that tissue is then demineralized. And you're able to see the effect of the underlying collagen on the crystals that formed on the surface. And what was found was that in 2 of those cases, the wild type and the osteopontin, one of them, you had quite a lot of clear directionality where the crystals aligned with the underlying support. But in 2 of them, you could see very clearly that there was very little alignment of the crystals within that biomineralized material, and they were then able to draw conclusions from that. This is an example of one example of STEM EELS work that was done by Angela Good. Actually, it's 2 examples of STEM EELS work done by Angela Good. The first one was looking at metal hip joints, where patients, when they get a replacement hip joint, sometimes they fail very quickly, or sometimes they can last for 15 years without any problem. So they were trying to understand what is it that's happening that causes all this pain. And one theory was that metal particles from the hip joint were going into the surrounding tissue. So they were investigating the tissue to see whether there were particles in it, and if there were particles, what chemical state they were in. And so on the left-hand side here, you can see a STEM EDX map where you can see each of the elements, the molybdenum, cobalt, chromium, oxygen maps here. And then on the right-hand side, you can see that similar information from oxygen, chromium, and cobalt, and they're able to map very specifically where each of those elements were, and then look at this at the specific coordination environments as well. In the middle here, this is an example where you need the very high energy resolution that's involved, that we have on our Titan microscope. So this is a carbon K-edge, an EEL spectrum of a carbon K-edge of a multi-wall carbon nanotube. The black line is of the pristine sample and the red line is of the oxidized sample. And you can see very clearly here that there is an extra peak in the oxidized sample. You can then map that across your nanotube. And so on the left-hand side, all the red dots are where the oxygen was picked up. In the middle, you can see the kind of the more crystalline, if you like, or the regular structure of the multi-walled nanotube. And then on the right-hand side, in the blue here, you can see all of the amorphous carbon material. So from this data here, you're able to differentiate between those different kinds of carbon materials. And this is part of the same figure, although actually taken from a paper by Suenaga, where he, using a monochromator, has been able to you can see the different coordination environment even within a carbon ring, and you can see different peaks in that carbon structure. So you can start to separate out very specific atomic coordination within a sample. Similarly, this was done by James Perkins. This is where you have STEM EELS data of high resolution STEM images, where you have a multi-layered structure of cerium and oxygen with and in one case, the layer is doped with samarium. You can see the high resolution image in the bottom left here. And then you can take a map across that sample. So first of all, they took a map of oxygen, cerium, and samarium. So you can map the profile of the elements across the sample. But then they were also looking at the difference between cerium 3 positive to cerium 4 positive in the material. And you can see these are the edge shapes. There's a shift in these peaks, and you can then map that across the sample as well. So here we have cerium 4 positive to 3 positive. And they're able to map that across the sample. Just a word on sample preparation. These images, some of it is to do with how good your electron microscope is, but a lot of it is to do with how good your sample is that is prepared. And something we'd be keen to do more of that used to be done in the past is low kV argon ion milling, even on samples that are prepared by FIB. When you do a very low kV argon ion mill, you make a much better surface on your sample, and so the data that you get out of your microscope is much better. Similarly, samples need to be kept very clean. There's a whole series of cleaning regimes that we can use to keep your sample clean in storage and to clean it before you put it into the microscope. So just in the last minute or two, just a word about our new facility that is starting to be installed at the moment. This is a very exciting project. We're still looking for a name for the facility, so if you have any suggestions, please drop them in the chat or email me. But this is going to be a cryo electron microscopy focused ion beam atom probe facility. And this is being installed at the moment. So the idea is that we want to investigate light elements such as carbon or sulfur, lithium, hydrogen that are very mobile under the electron beam. We want to be able to analyze them using atom probe and using aberration corrected TEM. Some of this work is being done elsewhere. If you do this at cryo temperatures, it also means that you're not moving, you're kind of immobilizing these materials that move very easily under the beam, and we can also do this in inert environments. So we'll prepare our samples in a cryoplasma fib. Those samples can then either be put directly into an atom probe under cryo temperatures, or they can be transferred into a glove box under an inert environment or cryo environment, and then either put back into the atom probe or put into the TEM. Alternatively, first of all, it can be analysed in the TEM, and the hope is that we can then put that back into our atom probe and do further analysis on it. So this is a very correlative technique. And this is just an example from Baptiste Gault, who has supplied this slide for me. This is our atom probe tip prepared in the fib. We can get our nanobeam diffraction pattern out of the TEM, look at grain orientation, take from our nanobeam diffraction pattern, we can start to create an orientation map, also a phase map in the TEM, and then you can see the atom probe information here. So this is what is currently being installed at the moment, is our plasma fib and a new Helios to replace our current Helios. And then in the next few months, we'll be installing a Thermo Fisher Spectra, which is going to have an ultra high, excuse me, is going to have an ultra high energy resolution probe corrector and direct electron detector. So we'll be able to have a full range out of applications for this. And this is just some of the promotional material that Thermo Fisher give with that. And alongside that, we'll also have a Talos microscope, so a lower end TEM for looking at the samples in advance of putting them into the microscope, but also to be doing a lot of in situ work with this instrument, as well as in our higher end TEM. Thank you very much for listening, and feel free to ask any questions at the end.
Thanks very much, Catriona. Very exciting.
This is my lunchtime talk about the mass spec and the AMS. Now, I'm taking a little different approach to everybody else. I'm just telling you how you can access the facility and what we've actually got at the facilities while you're here. So we're based at the MSRH over at the White City campus. And if you've got any questions, obviously put them on at the end, or you can just email me with my email address at the bottom there. So we've got 9 instruments, 5 of which are service, and 4/5, because we've got a new one coming, are fully open access. So open access just means you can use it yourself after you've had a training course. We've got a wide variety of techniques, so I'm not going to go through those because there's too many to cope with. But if you need to know what anything does, please feel free to email me. So we've got things like MOLDI, TGA, we can do low resolution and high resolution work, and we've got a DSC coming shortly. There's a link to our webpage as well, so if you go to Faculty of Natural Sciences at Imperial College, you'll be able to see what all the facilities we've got and what there is to get out of it. So I'm trying to get the next slide up. Yes. So how do you access the mass spec facility? So we currently use the PPMS system. So if you've already got a PPMS account or just an Imperial email address, you can either log in if you've already got an account with a different department, or create your own account if you don't already have an account. This can take up to 2 or 3 days to get approved, so don't worry if it doesn't happen straight away. So service work is where I can run stuff on your behalf. So if you go to PPMS and you want to request a service, then you can go to the order page. Here you'll be asked to submit your mass spec analysis sample. There'll then be another form which has all the information that I need to complete your work, and then I'll normally email the results to you. Now, these can either be dropped off or posted to MSRH, depends where you are, whether you're in White City or not. If you wanted to use any of the open access equipment, then you go to PPMS and you go to the request option. Now, the request option will mean that you need to fill in a little bit more paperwork, and there's slightly more paperwork than normal at the moment because of our COVID protocols, but it's all there. Once you have done the request, you'll get suitable dates and times for training, and then once trained, you can book your sessions via the calendar. So here you go to book, and you can select the total amount of time you need, what instrument you want to use, and then that's booked in for you. So just briefly about the Agilent measurement suite as well. So this is on the ground floor of the White City campus. So you can email the address down there on how to proceed with getting access to the Agilent measurement suite, or you can just email me and I'll put you in touch with the right person. So this is a multi-million-pound collaboration between Agilent and Imperial College. Now these are all self-service open access instruments, so there's no service available here. You're expected to be able to run your own samples after being trained. There's a variety of different types of instruments in the Agilent suite, just as LCMS, PrepLC, IRs, GPCs, that sort of thing. And again, if you go to the web page, you'll be able to see exactly what instruments are available. And Agilent also, on the Agilent Measurement Suite webpage, they do a various number of webinars, tutorials and workshops that you can work through as well if you wanted to do that yourself. So to access the AMS, you need to email the Agilent MSRS email address, and you'll be asked to complete a project pro forma, which just outlines what you want to do and what instruments you might be interested in learning how to use. You'll then be sent a link to iLabs for registration. Now, iLabs is an Agilent-owned booking system, so it works slightly differently to PPMS. Once you've registered for iLabs, you can go to request service and initiate a training request, and very much like the mass spec facility, you'll have a number of safety inductions to complete, and once you're trained, you can go to schedule equipment and book the calendar as you want. And as I said, the Agilent measurement suite is pretty much fully self-service and open access, so once you're trained, you'll pretty much be left on your own unless you request any help. So that was it really from my point of view. So just really quick there. So sorry about not being able to share my slides earlier, but if you need help or advice or you've got any questions, then please feel free to get in contact. So thank you very much.
Thanks very much, Lisa, and it's very useful to have that the procedure explained as well. So thanks. So next speaker is Dr. Irena Nevjestic. So we see you.
Yes. Can you see
Yep.
my slides?
I see your slides. Yep.
Okay.
Thank you.
So hi. I think just okay. So hi, my name is Irena, and I'm research facility manager of the Spinlab. I will show today which equipment is available in the lab and present few remarkable possibilities. So Spinlab is a multi-user state-of-the-art hub of magnetic characterization, which was established by 2 million EPSRC equipment grant. Spinlab includes equipment to study spin-based properties of materials in the strong and weak coupling regimes. And emphasis is put on the spin manipulation and their interaction using light and or electric bias. Spins are critical in many different processes, from charge transfer in catalysis or redox chemistry to transition metal chemistry and biological processes such as photosynthesis. Electronic spins can couple also to create a wide variety of magnetic phenomena in which we are interested. So Spinlab is in the Department of Materials, Royal School of Mines on the South Kensington campus at lower ground floor, and using office space that we have in the Department of Materials. It's easy to find it, so it's over here close by EM Suite. So if you just try to find Royal School of Mines lower ground floor, you can find it. It was established in 2019, and with various equipment and options implemented progressively. 2 main systems are now both up and running, and with all options available. So first available system is a magnetic property measuring system, also known as MPMS. It's very sensitive magnetometer used to measure extremely subtle magnetic fields down to 10 to the minus 8 EMU. Extremely sensitive magnetic measurements are achieved with superconducting pickup coils and the superconducting quantum interference device, also known as SQUID. And this is why this system is also known as SQUID magnetometer. The one in the Spinlab, it's quantum design latest MPMS-3 system with 7 Tesla superconducting magnet and a range of unique options. The system can operate between 2 Kelvin and 1000 Kelvin with a liquefier and a closed cycle cryogenic option. Helium consumption is minimized, and this is quite great feature at the moment with the ongoing shortage of helium. On top of that, users have zero contact with cryogenic liquid. Above room temperature system is using oven option, which is also available. Three measurements modes are available: DC, VSM, and depending on the sample or result that you would like to achieve, it will depend which one will be the best, but there are options. Hydrostatic pressure cells allows measurements under the pressure of maximum 1.3 gigapascals. And with ultra low field option, which actively cancels residual magnetic flux in the superconducting solenoid, samples can be measured in an accurate field up to 5 Gauss. And by zero field, this is defined as a field smaller than 50 milligauss. In the near future, the system will be coupled with a laser for measurements under optical excitation. On the right side here, you can see example of hysteresis loops recorded on various temperatures. So this particular one were not recorded at Spinlab, unfortunately, but we hope in the future to have something similar or even better. So hysteresis loops were recorded from 2K, the purple ones, up to 30K, the black ones, in steps of 4K in between. So this was done on a sample, a single molecular magnet, which is a candidate for high density data storage application. And these kind of hysteresis loops are first condition for that. A second system and technique that is available in the Spinlab is electron paramagnetic resonance or electron spin resonance, also known as EEPR or ESR. So this technique makes use of the magnetic moment of unpaired electrons to study materials. EEPR can give insight into structural information of the material, oxidation state of active sites, and quantitative information. So EEPR can detect subtle changes in the environment of unpaired electron, and it can also detect radicals in liquids. For short-lived free radicals, spin trapping can be used, which involves the addition of magnetic moment, usually one component, which reacts with a free radical to give a stable paramagnetic spin, which can then be easily detected and characterized by EEPR. On the right side here, you can see example of it. So the sample didn't show EEPR spectrum at start, but by adding a spin trap inside hydroxyl radical was detected. So spins present in transition metals, in catalysis, spintronics, also photoinduced and free radicals or charge generated in devices such as batteries. Batteries could be detected by EEPR and give really nice information about the materials. In Spinlab, we have Bruker X-band continuous wave Alexis E500 system. It has also similar closed cycle cryogenic option as for MPMS system, and it can operate between 1.8K and room temperature with the incredible stability for EEPR spectrometers of 10 millikelvin. The spectrometer is coupled with 20 Hz Q switch and the YAG laser, and with the optical paramagnetic oscillator, or known as OPO. This enables broadband operation between 110 and 2750 nanometers to study transient phenomena. Third available system, which is done via collaboration, is Hall effect system, and the equipment belongs to Professor Martin McLachlan and David Payne. So the one in the Spinlab is the Lakeshore 8400 series Hall effect system. It enables measurements of mobility, charge carriers, concentration, and resistivity of materials. With variable temperature stage, which is to be installed, it will allow seamless measurements between 10K and 1230K. And it also has high resistivity module which can measure up to 200 giga ohm resistance. The system can give insight into fundamental mechanisms of charge transport in a wide variety of semiconductor materials. So for more information and some measurements discussion, please contact me or Professor Sandrine Hoyts. Users can be trained to become independent users and to have more flexibility in scheduling and also performing experiments, but I can also do measurements for you if needed. Research groups are encouraged to have designated users to run samples for others within the group, and this is especially used for EPR measurements. And also all bookings can be done via PPMS system, where also users can request EPR training or MPMS training. But yeah, if you have any questions, please contact me.
Thank you very much. Great. So there is a question in the chat which we can get back to later on. Thank you, Robert. But we'll move on to the last speaker, Dr. Andrew White.
Right.
Thank you.
Small molecule crystallography is a technique for the determination of the atomic structure of crystalline materials by how they diffract X-rays. What you get as the output is a set of atomic coordinates telling you where each individual atom is. Typically, I'll work with materials of less than 200 non-hydrogen atoms, but that's not a fixed limit. The diffraction resolution we typically go to is 0.84 angstroms. The International Union of Crystallography mandates that for a publishable data set, you have to have collected a minimum of 98.5% of the symmetry unique data to a resolution of 0.84 angstroms. So that's what we go to, but we can go beyond that if required. If you're If you're wanting to study a protein sample, this is not quite the technique you want. There's a separate group in biochemistry who are specialised in looking at protein materials, and protein crystallography is a slightly different technique. But if it's what is called small molecules by contrast, let's say typically less than 200, then I'm the one to contact. We have two 4-circle diffractometers using different X-ray radiation wavelengths, one based on a piece of copper, one based on a piece of molybdenum. The copper having a wavelength of approximately 1.5 angstroms and the molybdenum 0.7 angstroms. These different wavelengths give different diffraction effects. Particularly absorption is one of them. If you want something you want to avoid, and you, depending on the material you've given, if it's fully light atom, it's okay with copper. If it's got metals in it which will absorb X-rays more strongly, you want to use molybdenum. One of the particularly useful effects, however, is that for copper radiation, you can start to see the difference in the diffraction from enantiomers. If you've got an optically pure compound and you want to know which enantiomer you've got, with the right circumstances, I would use copper-based radiation where the effect's largest. You can start to see the difference in the pattern of intensities you get depending on which enantiomer is present and get a better fit. So you can say in the end you've got the S enantiomer at that center rather than the R. Totally independent of any information you might have told me from the synthesis, I can tell you you've got the S. The particularly why you want to have the two wavelengths available. Other than that, the copper source gives you approximately 8 times more X-ray photons. It's a more intense source because of the approximately double wavelength. We regularly run the crystals at lowered temperatures using gaseous liquid nitrogen. We boil some liquid nitrogen and blow the gas over the crystal. So we're keeping the crystals, you can go down to about 100 Kelvin. Typically we do a 173 Kelvin, but that can be adjusted. Some samples you will find when you introduce them from room temperature into the low temperature, they don't like it and they crack. But if you put it into the sample, the low temperature stream at a higher temperature, and then gradually lower it, the crystals can survive. You just have to have enough crystals to be able to test where you can go down to before they crack. In terms of sample size, you don't want a crystal that's larger than the beam cross-section. And for the copper-based instrument, we have a maximum beam cross-section of 0.3 millimeters. For the molybdenum one, we typically use 0.8 millimeters, but we can go up to 1 millimeter if required. In terms of the lower limit, it's whatever I can mechanically handle, I will try. But you want to bear in mind that there's a strong correlation between the size of the crystal and how strongly it's going to scatter the X-rays, and therefore how long the experiment's going to need to be. And given that the internal recharging scheme is based on how long the experiment is, not a lot of people want to go in for a very long experiment. I would say that about 60% of the experiments I run are less than 2 hours. Right, how to use the service. The most important thing I want to stress at this point is getting the samples to me. However you do it, you have to bear in mind the college regulations for the transport of dangerous materials. It has to be packaged correctly, whether you're going to bring it yourself when the COVID protocols are relaxed, or you're going to get a courier to bring it. Has to be packaged properly following the college regulations, which you can find on the college website. Can't stress that enough. It is very important. You have to consider what would happen if your typically glass sample tube breaks. Will your liquid leak out? You have to have secondary containment and have the correct labels on the outside, etc., etc. If you don't send one packaged properly, even if it arrives here, I will say, no, not going to look at that, and send you a stern email saying do better. For anything else, you can contact me. My email address ajpw@ic.ac.uk, and just ask whatever question comes up to work out what information you want from the experiment, and we can discuss what is required. I think in the absence of my slides, that's where I draw it to a close. Thank you very much.
Thank you very much, Andrew. That was very clear, even in the absence of slides. Okay, thanks very much to all of the speakers today. I think we've had plenty of information and food for thought there, and also various styles which I think are useful in you know, thinking about the science, but then also the practicality. So I think altogether we've you know, thank you very much for covering a lot of info on sort of background science and also the practicalities of accessing the facilities. So the floor is open for questions to our speakers, and yeah, please raise your hands if you wish. There is a question for Irena, I think. Yeah, from Robert. Thank you.
Yeah.
Irena, thanks for your presentation. I had a question about the Hall effect system. So is that does that have a DC field, or is it capable of AC Hall as well?
Yes, it's both DC and AC. DC can go up to 1.67 Tesla, and AC I think up to 1.18 Tesla.
Right, thanks.
Thank you. And it should be pointed out that that particular piece of equipment is PI owned, but Spinlab has put an upgrade on it, and it's located in Spinlab, so that's why it's included here. A point from Adrian, just to re-emphasize that these talks will be posted on the LCN YouTube channel, and so you can catch up. So Maxi had a question.
Hi, yeah, thanks everyone for your talks. I have a more logistical question. So Sarah, a lot of what you talk about there sounds really interesting to my group. So I guess my question is really, how does it work at the moment in terms of access, especially in the light of COVID rules still? We are over in chemistry in White City. Is it possible for people to get trained, or is it more realistic at the moment to submit samples? How does it work?
Yeah, it's possible to get trained on the SIMS instrument. Yeah, just email me. My email is s.fearn@imperial.ac.uk, and we can talk through what needs to be done. And if it's a lot of samples, it's worth being trained if you're going to be using it regularly, and because you understand the data better and where it's all coming from, really. If it's one-off, then I can easily run that for you, and then you can work on the data yourself as well. So there's quite a wide range of flexibility really with accessing the instrumentation, but yes, we're open. Just email me and I can arrange times for people to come over and visit, etc.
Okay, great. So would it be okay basically if I ask a PhD student to get in touch and also discuss what exactly would be most suitable for what we are looking to do, because we're definitely not experts in what you've described earlier? So
no, absolutely. Okay. We'll start with it, and then we can arrange a face-to-face meeting to go over the things a bit more easily. So yes.
Fantastic, thank you.
Okay, we have a couple of questions from Milo. Do you want to get on mic, Milo, or should we read them out?
Well, so I thought we didn't have a cryo tomography holder included in the otherwise extensive facility, but maybe I've got the wrong end of the stick.
So we have multiple holders that we're getting. One is we have a vacuum transfer holder that can be done at cryo temperatures. So it's not a cryo transfer rod, but it is a cryo rod that can be transferred into the microscope under vacuum conditions. Whether it's a tomography rod, I would need to check whether that specific one is a tomography rod or not. We do already have a separate tomography rod. We are also getting a cryo transfer rod where you can transfer within liquid nitrogen rather than just a cooling rod. So you can, so you'll be able to transfer from, say, like a plunge-free sample into the microscope as well. I need to check whether the cooling vacuum rod is also tomography or not.
Yeah, I had the impression not, but maybe, as I say, maybe I've got it wrong. I guess it would be interesting to do things like looking at battery materials in electrolyte and then being able to freeze that out and then look at the tomography of that.
I need to check, but I suspect, so the rod is a Melbuild rod that we're getting, so I suspect that is not also a tomography rod. It's very difficult to get all of these in the ones.
Yeah, absolutely. I think Finn was looking into it and he said there's a Fishioni that does it, but he couldn't afford it. But I was just wondering.
Yeah, we did.
Because you mentioned tomography, I just thought maybe you had a plan for how to do it. But still
not under cryo conditions. I mean, we can do normal cryo tomography on the 2100F, but not on the new system with the current that we have, I think.
Okay, thanks.
Yeah, on that, I'd just like to point out. So we have holders to go across, like the Ferrovac holders to go across various facilities as well, including hopefully SIMS and so on. So we can really do multimodal. And I sent a link here to the LCN talks, and one of those talks is actually one from Baptiste Gold, who outlines a bit more on Atom Probe for anyone who's not had enough and wants to follow up from Catriona's last few slides. And so one more question from Milo for Sarah. brief suggestions for when to use LICE rather than XPS?
Yeah, so LICE gives you information of if there are elements sitting on the outermost atomic layer. LICE is ideal for that, and looking at the background signal from LICE, you can go to the second and the third atomic layer. So that's obviously closer to the surface than XPS, which averages on the whole over the first sort of top 5 nanometers. So you can sort of bridge that gap with LICE. We're not getting oxidation information, obviously, with LICE. It's just whether the element is there or not. You can do quantification with LICE as well. So, but there's quite strict protocol you need to go through in order to clean the surface and make sure you are looking at the surface. So it's sort of it's the region that's quite tricky to get at via XPS or SIMS, which tend to sort of look at the first, which miss the first 1, 2, 3 atomic layers of a crystalline or organic material or something like an ionic liquid. So that's when you should be using LICE if you want to sort of bridge that very near outermost surface of the sample. Does that help?
Yeah, okay, thanks very much. Oh.
Okay, so I think that's all we've got time for today. Thank you so much to everyone for talking today. That's super useful. And thanks for leaving your contact details so that those discussions can be followed up. And I look forward to lots of great nanoscience coming out of this. So thanks very much, and see you at the next. So this is the last LCN Monday lunchtime seminar of this time of the academic year, but there will be another joint LCN talk on Wednesday 2 till 3 with UCL and King's on the theme of spectroscopy, and one more symposium on nanomedicine on the 9th of June. So a few more LCN events to come, but in the meantime, thank you very much for today, everyone, and see you soon. Thank you.